In the summer of 1950, four men sat down to lunch at a laboratory in the mountains of New Mexico. They were physicists, among the most brilliant physicists alive at that moment in history, a moment when the study of matter and energy and the fundamental structure of reality had just produced the most destructive weapon human beings had ever built. These were men who understood the deepest known laws of the universe. Men who had spent years doing calculations that most human beings could not follow, arriving at conclusions that most human beings could barely accept. The conversation over lunch was casual, light, the kind of talk that scientists have when they're not working, wandering through ideas without agenda, following whatever thread seemed interesting that afternoon. They'd been talking about a cartoon. A New Yorker cartoon published that summer showed aliens stealing rubbish bins from the streets of New York City. It was absurd and funny, and the men at the table had been riffing on it, on flying saucers, on the recent wave of UFO reports in the newspapers, on what it would actually mean if something not from Earth were visiting our planet. And then the conversation moved on to other things, to whatever physicists talk about over lunch in the mountains of New Mexico in 1950. And then one of the men said something, not loudly, not dramatically, not with the air of someone who believed they were about to ask the most important question in the history of science. He said it the way you say something at a lunch table when a thought crosses your mind and you decide to speak it rather than let it pass. He said, "But where is everybody?" The man was Enrico Fermi. Fermi was not someone whose questions were easy to dismiss. He had built the first nuclear reactor in a squash court beneath the University of Chicago. He had done theoretical work that would underpin quantum mechanics for decades. He had a reputation among colleagues for thinking about problems from first principles, for cutting through complexity and getting to the essential structure of a question with a directness that left other brilliant people feeling slightly embarrassed at how long it had taken them to see what Fermi saw immediately. So when Fermi asked a question, people paid attention. And the question he asked that afternoon, framed casually, offered almost as an aside, was one that the more you turned it over in your mind, the more it refused to stay casual. Where is everybody? He was not asking about the cartoon. He was not asking about the UFO reports. He was asking about something far larger, something that the mathematics of the universe, as he understood it, made genuinely difficult to explain. The universe is approximately 14 billion years old. Our galaxy alone contains somewhere between 200 and 400 billion stars. Many of those stars are older than our sun by billions of years, some of them by 5 billion years, some by 8 billion, long enough for any civilization that emerged around them to have had not just centuries of technological development, but geological epochs, long enough to have solved problems that we have not yet learned to ask, long enough to have built things, done things, gone places that exist so far beyond our current imagination that we would struggle to recognize them as the products of intelligence at all. And yet, the sky is quiet. No signals, no visitors, no megastructures detectable around distant stars, no evidence in any direction, at any frequency, from any instrument we have built, of anything out there doing anything that would mark it as the product of a mind. Fermi understood the mathematics of this. He understood probability. He understood the sheer scale of what the numbers implied. And so when he looked up from the table and said, "But where is everybody?" the men around him understood that this was not a casual observation. It was a problem. One of the men at that table, Herbert York, remembered it decades later. He recalled the laughter that followed Fermi's question. Not dismissive laughter, but the laughter of people who had just had something obvious pointed out to them in a way that suddenly made it seem not obvious at all. The laughter of recognition, of suddenly seeing something that had been sitting in plain sight, waiting for someone to name it. The question became known as the Fermi Paradox. A paradox because the mathematics of the universe, the age of it, the size of it, the number of opportunities it has had to produce intelligence, seems to point overwhelmingly toward the conclusion that we should not be alone. That the galaxy should, by any reasonable calculation, be teeming with life at various stages of development, that some of it should be far older and far more capable than us, that the evidence of its existence should be everywhere, and the observation, the blunt, unarguable, persistent observation is that we have found nothing, not a signal, not a probe, not a structure, not a shadow, not a trace. The mathematics says the universe should be full, the sky says it is empty. Those two things cannot both be true. And 70 years after a physicist asked a casual question over lunch in the mountains of New Mexico, we have not resolved the contradiction. If you find that unsettling, you should. Because the implications of this paradox, whichever direction you follow them, lead somewhere that changes how you think about what we are, where we are, and how long we are likely to last. If this is the kind of content that pulls you somewhere you did not expect to go, subscribing to The Cosmic Depth takes 2 seconds, and we post new documentaries every few days. Because this question does not end with the mathematics. It ends somewhere much closer to home. And we're going to go there slowly, carefully, and all the way to the bottom. Start with a single number, 200 billion. That is a conservative estimate of the number of stars in the Milky Way galaxy alone. 200 billion suns, some smaller than ours, burning cool and red for trillions of years. Some larger, burning bright and brief. Most of them, by the best current estimates, surrounded by planets. Not some of them, most of them. We know this now in a way that Fermi could only have estimated in 1950. Since the launch of the Kepler Space Telescope in 2009, astronomers have confirmed the existence of thousands of exoplanets, planets orbiting stars beyond our sun, and used that data to calculate how common planetary systems are across the galaxy. The answer that came back was not what the most cautious scientists had hoped for. Planets are ordinary, not rare, not exceptional, not the product of some unusual cosmic circumstance that makes our solar system a special case. Ordinary, the default, the expected outcome when a cloud of gas and dust collapses around a forming star. And among those planets, a significant fraction orbit their stars in what astronomers call the habitable zone, the region where liquid water can exist on a planetary surface, the region where chemistry can do what chemistry does on Earth. Build complexity, build molecules, build the conditions that on this planet eventually produce something capable of sitting in a dark room late at night, wondering if it is alone. The estimates vary. but the most widely cited figures suggest that there are somewhere between 8 billion and 40 billion Earth-sized planets in the habitable zones of sun-like stars in the Milky Way alone. 8 billion in one galaxy. And the observable universe contains approximately 2 trillion galaxies. Do that multiplication if you want. The number you arrive at is so large that it has no meaningful referent in human experience. It is not a number that corresponds to anything you have ever seen or touched or been able to hold in your mind. It is simply a sequence of digits that represents more chances for life to have emerged than there are atoms in your body. Now add time. The universe is 13.8 billion years old. Our sun formed approximately 4.6 billion years ago. That means there were stars burning in this galaxy for over 9 billion years before our sun ignited. Planets forming around those stars, habitable zones existing around those stars. 9 billion years of opportunity before Earth existed. If life emerged around even one of those earlier stars, if intelligence evolved even once in the 9 billion year head start the galaxy had on us, that civilization would have had 9 billion years more than us to develop. Think about what 9 billion years means in terms of technological development. We went from the Wright brothers to the moon in 66 years. We went from the first radio transmission to interplanetary spacecraft in less than a century. We are currently in the earliest stages of our technological adolescence, beginning to develop artificial intelligence, genetic engineering, and the theoretical foundations for technologies we cannot yet build. Now imagine a civilization that has been developing for not a century, not 1,000 years, not 1,000,000 years, 9 billion years. The gap between what they would be capable of and what we are capable of is not a gap that can be bridged by imagination. It is simply too large. A civilization 9 billion years more advanced than us would be to us what we are to the bacteria living in the soil of a garden, not hostile, not friendly, simply operating at a level of complexity and scale that makes the comparison almost meaningless. And this is where the Drake equation enters the picture. Frank Drake was an astronomer who, in 1961, 11 years after Fermi's lunch question, tried to turn the paradox into mathematics. He wrote an equation that broke down the question of how many communicating civilizations might exist in the galaxy at any given time into its component parts. The equation multiplied together a series of fractions and rates: the rate of star formation in the galaxy, the fraction of stars with planetary systems, the fraction of those planets that could support life, the fraction that actually developed life, the fraction where life evolved into intelligence, the fraction of intelligent species that developed detectable technology, and finally, the most uncertain and in many ways the most important variable: the average length of time a communicating civilization survives before it goes silent. Drake did not design the equation to produce an answer. He designed it to organize ignorance, to identify which questions needed to be answered before the bigger question could be addressed, to give scientists a framework for thinking about a problem that was so large and so poorly constrained that without a structure, it would dissolve into speculation. But something interesting happens when you plug numbers into the Drake equation using the best current estimates for each variable. Even with conservative values, even when you assume that life is relatively rare, that intelligence is rarer still, that most civilizations do not survive long enough to become detectable. The equation tends to produce answers that suggest there should be at least some other civilizations in the galaxy. Not thousands, not millions, but some, a handful, enough that the silence becomes statistically strange. And when you use more optimistic values, values that reflect the extraordinary abundance of planets we now know about, the resilience of life we've observed in extreme environments on Earth, the speed with which life appeared on our own planet after it formed, the equation starts to produce numbers that make the silence not just strange, but almost inexplicable. Life appeared on Earth within a few 100 million years of the planet forming. In geological terms, almost immediately. As soon as the conditions existed for chemistry to do its work, something started doing it. This suggests that life, given the right conditions, is not a miraculous accident waiting billions of years for the right molecule to assemble by chance. It is something that happens quickly, reliably, whenever the conditions permit. If that is true across the galaxy, if life emerges quickly wherever liquid water and the right chemistry exist, then the number of planets where life has existed at some point in the history of the Milky Way is not small. It is enormous. And yet the sky is quiet. This is the weight of the paradox when you hold the mathematics in one hand and the observations in the other. The mathematics, at its most generous, suggests a galaxy alive with intelligence at various stages of development. Ancient civilizations that have had billions of years to spread, to build, to leave marks on the universe that should be visible across interstellar distances. Younger civilizations like ours, just beginning to reach out with radio waves and telescopes and the first tentative probes sent toward nearby stars. The observations suggest none of it. No signals in 70 years of searching. No megastructures detected around nearby stars, despite dedicated observation programs specifically designed to find them. No signs of stellar engineering. No evidence of large-scale energy harvesting around any of the hundreds of billions of stars we have cataloged. No visitors, no probes, no artifacts. The physicist Michael Hart formalized this in 1975 with what is sometimes called Hart's fact. The simple, blunt observation that no extraterrestrial civilizations have been detected and none have visited Earth in any way we can verify. It sounds obvious. It is obvious. And yet, in the context of what the mathematics suggests should be out there, it is one of the most profound facts in the history of science. We have looked. We are looking. We will keep looking. And so far, in all the looking, we have found nothing. The silence has a weight to it that grows heavier the more carefully you calculate what should be breaking it. There are answers to this silence. Some of them are comforting, some of them are not. We are going to go through all of them, starting with the ones that let you sleep. There is a version of the answer to the Fermi Paradox that lets you close your eyes at night without difficulty. Several versions, actually. Scientists and philosophers who have spent time with this question have produced a range of explanations for the silence that do not require anything catastrophic. Explanations that suggest the absence of contact is not evidence of absence, that the quiet sky is not a warning, that we're simply earlier or smaller, or looking in the wrong places, or asking the question in the wrong way. These explanations deserve to be taken seriously. Some of them are genuinely compelling, and we're going to go through them carefully because the only honest way to approach the darker answers is to first establish that the comfortable ones do not fully hold. The first and perhaps most intuitive explanation is what scientists call the rare earth hypothesis. The argument goes like this: life on Earth did not simply require liquid water and the right chemistry. It required an extraordinary convergence of specific circumstances. Circumstances that may be far less common across the galaxy than the raw numbers of planets suggest. Consider what Earth actually needed: a star of exactly the right size and stability, not too large to burn out before life could evolve, not too small to bathe its planets in lethal radiation. A position in the galaxy neither too close to the dense, radiation-drenched galactic center, nor too far out in the sparse, metal-poor outer rim, where the building blocks of rocky planets are scarce. A planet of exactly the right mass, large enough to hold an atmosphere and generate a protective magnetic field, small enough that gravity does not crush the chemistry of life before it begins. A large moon. This is one that people rarely think about. Earth's moon is unusually large relative to its host planet, almost certainly the result of a catastrophic collision early in the solar system's history between the proto-Earth and a Mars-sized body. That collision gave Earth a moon large enough to stabilize our planet's axial tilt. Without it, Earth's axis would wobble chaotically over millions of years. Shifting climates so dramatically and so rapidly that complex life might never have had time to establish itself before the conditions it depended on shifted beneath it. A gas giant in the outer solar system. Jupiter sits in the outer solar system like an enormous gravitational shield, its mass deflecting or capturing a significant fraction of the comets and asteroids that would otherwise rain down on the inner planets. Without Jupiter, Earth would likely have experienced impact events orders of magnitude more frequent and more devastating than those it has actually endured. Life would have been reset repeatedly, never accumulating the unbroken billions of years of continuous evolution it needed to produce anything complex. Add to all of this the specific timing of Earth's development, the Great Oxidation Event, the Cambrian explosion, the 5 mass extinctions that each time cleared the stage for new forms of life to diversify into the space left behind. And what you begin to see is that the path from chemistry to technological civilization is not a smooth, inevitable ramp. It is a series of narrow doorways, each one requiring specific conditions to be in place at exactly the right moment. The rare earth hypothesis argues that the combination of all these requirements, the right star, the right position, the right planetary mass, the right moon, the right gas giant neighbor, the right timeline of catastrophes and recoveries, is so improbable that Earth-like planets capable of producing technological civilizations may be genuinely rare, perhaps vanishingly rare. Perhaps rare enough that in a galaxy of 200 billion stars, we are the only ones. It is a comforting thought in one sense. It explains the silence without invoking catastrophe. We are alone not because others have been destroyed, but because the conditions required to produce us were extraordinarily specific, and we simply happened to be the lucky combination. But the rare Earth hypothesis has problems. The same argument that complex life requires very specific conditions was once applied to the existence of planets at all. Before the Kepler telescope, some scientists argued that stable planetary systems might be rare. Then we discovered that planets are ordinary. The same argument was once applied to the existence of liquid water beyond Earth. Then we found evidence of subsurface oceans on Europa and Enceladus, and water-bearing minerals on Mars, and water vapor in the atmospheres of exoplanets dozens of light years away. Every time we have assumed that the conditions for life are rare, the universe has turned out to be more permissive than we expected. Life on Earth has been found in environments: deep ocean hydrothermal vents, highly acidic hot springs, Antarctic ice sheets, the cooling cores of nuclear reactors. That would have been considered completely inhospitable not long ago. The universe may be stranger and more accommodating than the rare Earth hypothesis requires it to be. The second comfortable explanation is the communication gap. Perhaps civilizations are out there, perhaps many of them, but the methods they use to communicate, or the methods they have long since moved past, are simply not the ones we are looking for. We have been searching primarily in the radio frequency range because radio waves travel at the speed of light, pass through interstellar gas and dust without being scattered, and can be generated with relatively modest technology. In 1960, Frank Drake pointed a radio telescope at two nearby stars and listened. We have been listening in various forms ever since. But a civilization millions of years more advanced than us might have moved past radio the way we have, moved past telegraph. They may be communicating through means we have not yet conceived of: quantum entanglement, neutrino beams, gravitational wave modulation, some principle of physics we have not yet discovered. We would be listening at the wrong frequency for a signal transmitted on a channel we do not know exists. It is the equivalent of a civilization in the year 1800 scanning the sky for the light flashes of signal mirrors, while modern cities broadcast their existence in radio waves the 1800s. Civilization had no concept of and no instruments to detect. We may be the civilization with the signal mirrors, looking for something in the visible spectrum while the real conversation is happening somewhere we have not yet learned to look. This explanation is genuinely difficult to dismiss. The history of our own technological development suggests that our current methods of communication will look primitive within a few hundred years. Expecting an advanced civilization to still be using radio is arguably as naive as expecting them to be using drums. The third comfortable explanation is the most straightforward. We have not been looking long enough, or hard enough, or with sensitive enough instruments. Systematic radio searches for extraterrestrial signals have been underway for roughly 60 years. 60 years in a galaxy 14 billion years old. 60 years of looking at a small fraction of the sky, at a limited range of frequencies, with instruments that, compared to what we will have in a century, are relatively primitive. The breakthrough. Listen program, the most comprehensive CD effort ever mounted, has examined around 1 million stars. 1 million sounds like a large number. In a galaxy of 200 billion stars, it is less than 1/100th of 1%. We have surveyed a vanishingly small portion of our own galaxy and found nothing. and some people are surprised by that result. The argument here is one of simple patience. We are a young species with young instruments at the very beginning of our search. The absence of a result after 60 years is not evidence of absence. It is evidence of 60 years of looking, which is not nearly enough. These three explanations, rare earth, communication gap, insufficient search, are the ones that allow a certain kind of optimism about the universe. The ones that suggest the silence is a temporary condition of our own limitations rather than a permanent feature of the cosmos. They are worth holding on to because the alternative explanations do not offer the same comfort. Not even close. The comfortable explanations have a quality that the honest part of your mind eventually notices. They explain the silence by pointing to our limitations. We are not looking correctly. We are not looking long enough. The conditions for life are rarer than we think. Each of these answers locates the problem in our youth, our ignorance, our instruments, our assumptions. They leave the universe itself benign and full of possibility. The darker explanations do something different. They locate the problem in the universe. The most famous of the darker answers has a name that sounds almost bureaucratic for something so disturbing: the Great Filter. The idea was developed by economist Robin Hanson in 1998, and it begins with a simple observation that should by now feel familiar. The universe is old, it is vast, it is full of planets, and it appears to be empty of detectable intelligence. Something, somewhere in the chain from simple chemistry to spacefaring civilization, is extraordinarily hard to get through. Something filters out almost everything before it reaches the point where it would be visible to us. That filter exists. The silence proves it exists. The question, the only question that matters, is where in the chain it sits. If the filter is behind us, we are fortunate beyond any reasonable expectation. Perhaps the genuinely difficult step is the origin of life from non-living chemistry. Perhaps the gulf between a soup of organic molecules and the first self-replicating structure is so vast, so improbable, that it has happened only once in the observable universe. Or perhaps the difficult step is the jump from simple, single-celled life to complex multicellular organisms, a jump that took nearly 2 billion years on Earth and may require such specific conditions that it almost never happens elsewhere. If the Great Filter is one of these early steps, if the thing that is almost impossibly hard is already behind us, then our existence on the other side of it is remarkable. We made it through something that almost nothing else did. The silence around us is the silence of a universe where almost everything got stuck at a step we somehow cleared. We are, in that reading, extraordinarily lucky. This is the version that lets you sleep. But there is another version. What if the filter is not behind us? What if the extraordinarily hard step, the thing that almost no civilization survives, is something that happens at approximately our level of development, or slightly beyond it? Consider what we know about ourselves. We are a species that in the span of roughly a century developed nuclear weapons capable of ending complex life on this planet. We are a species that is currently destabilizing the climate system that sustains our civilization. We are a species developing artificial intelligence whose long-term implications we do not fully understand. engineering biology whose consequences we cannot fully predict, and accumulating the capacity to cause harm at scales that were not physically possible for most of our history. We are, in short, a species that has acquired tremendous power considerably faster than we have acquired the wisdom to use it without destroying ourselves. What if that is the filter? What if the point at which a civilization develops the technology to reach beyond its home planet is precisely the point at which it also develops the technology to destroy itself? And the overwhelming majority of civilizations that reach that point choose, through accident or intention or simple civilizational dysfunction, the second path rather than the first. The silence of the universe would then be explained not by the rarity of intelligence, but by its fragility, not by the difficulty of getting to where we are, but by the near impossibility of surviving past it. In that reading, the empty sky is not evidence of our uniqueness. It is a graveyard full of civilizations that reached approximately our level, looked out at the universe with instruments not unlike ours, asked questions not unlike the ones we are asking, and then, in one way or another, went quiet. This is the great filter at its most disturbing. And it is genuinely difficult to construct an argument that makes it implausible. We have no evidence that civilizations routinely survive their own technological adolescence, because we have found no civilizations to examine. We have considerable evidence from our own history that the combination of expanding power and limited wisdom is one of the most dangerous conditions a species can find itself in. The second of the darker answers comes from a Chinese science fiction writer named Liu Cixin, who gave it a name that has since entered the vocabulary of anyone who thinks seriously about the Fermi Paradox. The dark forest. The idea is this: imagine the universe as a dark forest. Every civilization in it is a hunter, moving quietly, carefully, trying not to make noise. Not because the forest is empty, but because it is full of other hunters. And in a universe of finite resources and unbounded potential for conflict, any civilization that announces its presence to the others is taking an existential risk, because you cannot know the intentions of whatever hears you. You cannot know whether they are benign or hostile. You cannot know whether they have resources sufficient to eliminate you before you could defend yourself. You cannot know whether their value system bears any resemblance to yours. All you know in the dark forest is that you exist and that others might exist, and that the cost of being wrong about their intentions is everything. The rational strategy in the dark forest is silence. Every advanced civilization having reasoned through this calculation goes dark. They do not broadcast, they do not transmit. They listen carefully and quietly, and if they detect another civilization that has not yet understood the rules of the forest, they face a terrible decision. Liu Cixin's dark conclusion, the conclusion his novel follows to its logical end, is that the decision an advanced civilization makes upon detecting a younger, noisier civilization is to eliminate it before it becomes a threat. This is, of course, a story. Science fiction extrapolated into philosophy. But the underlying logic is not easy to dismiss with the comfortable assumption that advanced civilizations are necessarily peaceful. We have no evidence for that assumption. We have considerable evidence from our own history that the encounter between a technologically superior civilization and a less developed one tends to end badly for the less developed one, regardless of the intentions of either party. If the dark forest is the answer to Fermi's question, then the wow signal was not a message. It was a mistake. And the silence that followed was not abandonment. It was someone realizing they had made a noise in the forest and going very, very quiet. There is a third, darker answer that does not require hostility or self destruction. It is in some ways the most unsettling of all because it requires the least dramatic assumption. Perhaps civilizations simply turn inward. A species that develops sufficiently advanced technology, artificial intelligence, virtual reality, the ability to simulate experience at arbitrary levels of richness and complexity, may find that the universe outside its home system holds nothing more compelling than the universe it can construct inside its own mind. Why spend the unimaginable energy required to cross interstellar distances, to colonize hostile environments, to build structures visible across light years, when you can build a simulated cosmos of equal richness inside a computer the size of a small moon, running at 1,000,000 times the speed of physical time, containing experiences of unbounded variety and depth? In that reading, the galaxy is not empty. It is full of civilizations that have retreated behind their own event horizons, not destroyed, not silenced by fear, but simply no longer interested in the physical universe in any way that would produce signals we could detect. They are not out there. They are in there. And from the outside, the result looks identical to extinction. These are the answers that do not let you sleep easily. And the honest reason they are harder to dismiss than the comfortable ones is that each of them is consistent with everything we observe. The great filter does not contradict any data. The dark forest does not contradict any data. The inward turn of advanced civilizations does not contradict any data. Neither do the comfortable answers. The silence is consistent with everything, which means it resolves nothing, which means we have to live with the question still open and look at whatever evidence we actually have, rather than the evidence we would prefer to have. There is one thing worth saying before we move to what our own discoveries are beginning to suggest. These are not merely abstract philosophical positions. The answer to the Fermi Paradox, whichever answer turns out to be correct, has direct implications for what happens next, for our species, on this planet, in this century. If the great filter is behind us, we are in an open universe, full of silence, yes, but a silence born of rarity, not destruction. A silence we may eventually fill. If the great filter is ahead of us, then the most important question facing our species right now is not whether we can reach the stars. It is whether we can survive long enough to try. We have been talking about the Fermi Paradox as a theoretical problem, a mathematical puzzle, a philosophical exercise, something that exists in the space between the numbers of the Drake equation and the quiet of the radio telescopes. But over the last few decades, something has been happening that changes the texture of the question. We have been finding things, not the things we were looking for, not the clear, unambiguous signal that resolves the paradox in one direction or another, but things that sit at the edge of what we can explain, things that keep arriving in our data without ever quite declaring themselves, and that collectively paint a picture of a universe that is, at minimum, more complicated than the silence suggests. You already know some of them. In August 1977, a radio telescope in Ohio detected a signal 72 seconds long at the hydrogen line frequency, with characteristics that matched the theoretical profile of an intentional interstellar transmission more closely than anything detected before or since. It has never been explained. It has never been repeated. Jerry Amon circled it in red pen and wrote one word. And 45 years later, that word still stands as the most accurate summary of what any serious scientist feels when they examine the data carefully. Something happened on that night that our best explanations have not yet fully accounted for. Fast radio bursts are another piece of the picture that will not stay still under examination. These are millisecond pulses of radio energy arriving from cosmological distances, from galaxies billions of light years away, with an energy output in that single millisecond equivalent to what our sun produces across days or weeks. They were first detected in 2007 and initially dismissed as instrument artifacts. Then more were found, then hundreds, now thousands, cataloged and studied and still not fully understood. Some repeat, most do not. The repeating ones show patterns, periodicities, structures that certain researchers have noted are difficult to reproduce with purely natural mechanisms. Not impossible, difficult. The natural explanations are plausible. They are also, in several cases, constructed around a single event that has never been replicated under controlled conditions, which is not the usual standard for a settled scientific question. Then there is Oumuamua, the object that entered our solar system in 2017 from interstellar space, accelerated away from the sun in a manner inconsistent with any comet-like outgassing anyone could detect, exhibited a shape unlike any natural object previously observed, and then departed back into interstellar space before we had gathered enough data to say anything definitive about what it was. The Harvard astronomer Abraham Loeb, not a fringe figure, not someone with a reputation for sensationalism, concluded that the most parsimonious explanation for Oumuamua's behavior was that it was an artificial object, not certainly artificial, possibly, consistent with being artificial in ways that natural explanations struggled to match. He was criticized for saying so, loudly and repeatedly, by colleagues who felt that invoking extraterrestrial technology violated the principle of preferring simpler explanations. But here is the thing about that criticism that is worth sitting with quietly. The simpler explanation depends on what you are allowed to assume. If you are allowed to assume that interstellar objects of a type never previously observed behave in ways that have never been observed before, for reasons that invoke physical processes that have never been directly measured in this context, then yes, the natural explanation is available. If you are required to explain the specific combination of observed properties using processes that have actually been measured and verified, then the explanation becomes considerably less simple. We are not saying Oumuamua was artificial. We are saying it was strange. And strange things in data deserve more attention than they sometimes receive, particularly when strangeness accumulates. Because that is what is happening. The strangeness is accumulating. The exoplanet surveys have now confirmed thousands of worlds in habitable zones. Some of them orbit stars that are billions of years older than our sun. Some of them have atmospheres that, when analyzed by the James Webb Space Telescope, show chemical signatures that are At minimum, worth examining more carefully, not definitive, not proof of anything, but inconsistent with purely geological explanations in ways that keep the relevant scientists publishing papers and attending conferences and not sleeping as well as they used to. There is a star called KIC 846 2852, sometimes called Tabby's star, that dims irregularly in patterns that no proposed natural mechanism has fully explained, in ways that were first publicly noted because a group of citizen scientists looking at Kepler data noticed something the automated systems had classified as unremarkable. Something is blocking the light of that star periodically, in irregular patterns, in ways that comet swarms and dust. Clouds and all the standard explanations have struggled to fully account for. We do not know what it is. We are looking. None of these individual data points proves anything. Each of them, taken alone, can be explained away with sufficient creativity and sufficient willingness to invoke unusual natural phenomena. The Fermi Paradox remains unresolved. The sky remains quiet in the sense that matters, no confirmed, verified, repeatable signal of extraterrestrial intelligence has been detected. But what these data points do collectively when you lay them beside each other in the dark and look at them honestly is suggest that the universe may not be as empty as the silence implies. That something may be out there, or may have been out there, that our instruments are only beginning to be sensitive enough to detect. That the silence is not the silence of a void. It is the silence of a forest at night, where the absence of obvious sound does not mean the absence of life, where something is almost certainly moving between the trees, where your eyes have not yet adjusted enough to the dark to see what is there. We are a young species with young eyes. They are adjusting. Come back for a moment to that lunch table in New Mexico. Enrico Fermi setting down his fork, asking a question that sounded casual and was not. But where is everybody? We have spent this entire documentary following that question outward, into the mathematics of probability, into the catalog of proposed explanations, into the data that sits at the edges of what we can explain. We have looked at the comfortable answers and the disturbing ones. We have looked at the things our instruments have found that refuse to sit quietly in the file marked understood. And now it is time to bring the question back, not outward, inward. Because the Fermi Paradox is not only a question about the universe, it is a question about us. And the most important thing it might be telling us has nothing to do with alien civilizations at all. Think about the great filter one more time. If the filter is ahead of us, if the extraordinarily difficult thing that almost no civilization survives is the transition from a planetary species to something beyond, then what we do in the next century matters in a way that is almost impossible to overstate. Not for us alone, for the question itself. We are, as far as we know, the only candidate currently on the field. The only civilization we have evidence of that is actively engaged in the process of deciding what kind of species it wants to be. Whether it will direct its technology toward its own destruction or toward something that persists. Whether it will solve the problems that are currently accumulating faster than our institutions are moving to address them. If we fail, if we become another data point in the silence, another civilization that reached approximately this level and then went quiet, Then the paradox deepens for whoever eventually comes after us, if anyone does. If we succeed, if we navigate this transition and become a civilization that endures, that learns, that eventually reaches beyond this planet, then we become potentially the answer to the question for someone else, the signal in someone else's sky, the evidence that the filter can be passed. This is not a comfortable thought in the motivational sense. It is not the kind of thing you put on a poster. It is the kind of thought that arrives at 3 a.m. when the other thoughts have gone quiet, and you are left with the actual weight of what it means to exist at this specific moment in the history of intelligence. We are here at the hinge. The point where the question of whether intelligence survives its own development is being actively answered by us in real time through the choices we make individually and collectively about what we value and what we are willing to do and what we are willing to sacrifice and what we are willing to protect. The universe has been running this experiment for 14 billion years across trillions of planets. And as far as we can tell, we are the only result that is currently conscious of the experiment. That is either the loneliest thought you have ever had, or the most clarifying one. The Fermi Paradox does not resolve neatly. It does not have a satisfying conclusion that closes the question and lets you file it away. The silence remains. The mathematics remains. The disturbing gap between what probability predicts and what observation confirms remains exactly as wide as it was when Fermi set down his fork. But the question itself, the act of asking it seriously, of following it all the way to the places it leads, of refusing to let either the comfortable or the disturbing answers satisfy you before you have looked at them honestly. That act is not nothing. It is, in fact, one of the most distinctly human things we do. We are a species that asks questions whose answers we may never live to know. We point telescopes at the dark and listen for decades for a signal that may never come. We send golden records into interstellar space addressed to recipients we cannot name. We build equations that organize our ignorance and then spend generations trying to fill in the variables. We sit at lunch tables in mountain laboratories and ask, but where is everybody? And then we spend the rest of our lives and the rest of our civilization's life, and perhaps ultimately the rest of our species' life, trying to find out. The silence has not broken yet, but we are still listening. And as long as we are still listening, as long as there is still a species on this planet pointing instruments at the dark and asking the question, then the silence has not won. Keep asking, keep looking, keep going. If this changed the way you see the silence between the stars, the cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.